SwayamPrabha. Digital India. Educated India.
Okay, last we have discussed about the development of boundary layer, how a boundary layer flow develops from the start of the motion, and we have also seen that the distance to within which the viscous effect, that is the diffusion of vorticity or velocity, occurs is of the order of square root of or inverse square root of Reynolds number, and on that basis we have made some order of magnitude analysis and derived approximate form of the boundary layer equations, or what is known as the boundary layer approximations, the equations that are valid for boundary layer. We would like to see the same equations again through normalization. We would like to normalize the equations properly. So, let us have the Navier-Stokes equations. We will once again derive the equation. So, this is actually nothing new, whatever we have done yesterday, we will be doing the same thing, but using a little different approach. We will make this approximation through normalization. We have the incompressible Navier-Stokes equations, which can be written as the x component of momentum equation, which is du dt plus the y component of momentum equation, and the mass conservation or volume conservation equation or continuity equation. Now, we would like to normalize or non-dimensionalize these equations. Now, once earlier we non-dimensionalized these equations, where we used some characteristic length and characteristic dimensionalize each of these terms. If you remember, for velocity we used u infinity, and for x, y, z coordinate length we used L. But in discussing boundary layer equations, we have seen that even though the characteristic length in the streamwise direction is L, the characteristic length in the normal direction is not really L. It is of the order of inverse square root of Reynolds number. So, this time we will use appropriate length scale and velocity scale to normalize these equations, and we normalize or non-dimensionalize this equation as follows. So, the non-dimensional x prime is as usual x by L, where L is the reference length in the streamwise direction. Y prime is not y by L, but r e to the power minus half into L, because the length in the normal direction or the thickness of that boundary layer is of the order of inverse square root of Reynolds number. So, that we that is y by delta, where the delta is the boundary layer thickness of the or the order of the boundary layer thickness. U bar will make it u by u e, where as before that any parameter with a subscript e means that it is the value at the edge of the boundary layer, or it is the inviscid flow solution, the inviscid flow solution. Just like y prime and for pressure we normalize following this. And T of course you can T prime of course you can think as T by L by U e. Now, if you substitute these parameters, what happens to the equations? If we substitute these in the equations, the Navier-Stokes equations which we have wrote it here, we substitute these non-dimensional parameter here. what we will be getting is the x component of momentum equation in this normalized form remains almost the same, only 1 by R e comes here and the other terms have no coefficient. The y component of momentum equation comes as and the continuity chains remain as it is. Now, see, if we assume that Reynolds number is very large, so that 1 by R e approaches 0, and in that situation all the derivatives are finite, then we can see that from here we can neglect all these terms. In this equation this term, okay, and in this equation all these terms except this, the pressure. So, what do we get? one thing is clear from here, that the equation for very large Reynolds number do not contain the parameter Reynolds number. There is no Reynolds number in the equations. So, it is obvious that the solution, at least in this form, solution of these equations, where your parameters are u prime, b prime, p prime, will not contain Reynolds number, because the Reynolds number do not appear in the equations, neither do they appear in the boundary conditions. So, in the limit of very large Reynolds number, the Reynolds number do not appear in the equations in the non dimensional form, neither do they appear in the boundary condition. The boundary condition is simple, that on the solid wall there is no slip. At the edge of the boundary layer, the two solutions will merge smoothly. And one more thing that is also required to solve these equations, that is, at some x location, you have to provide the solution. For a steady flow case, at some location, that is at some x, you have to give the solution. Then you can get the solution for x greater than that value. If your solution is given at, say, at x equal to x naught, then you can get the solution for x greater than x naught. That is because of the nature of the boundary layer equations. The boundary layer equations in this form, or the form that we had last day, they are parabolic in nature. So, you have to give an initial solution. So, if we consider steady flow where there is only x and y, so some x location is the initial condition. At some x location, you have to give the solution. Only then you can find the solution. Not so at low Reynolds number, but at very high Reynolds number, the solution do not contain any reference to Reynolds number, and even if the Reynolds number changes something, the solution will remain same. Meaning, say as an example, this may not be large, but usually what we find is quite large enough for airfoil type of problems, whether your Reynolds number is say 10 to the power 7 or 10 to the power 8 or 10 to the power 9, the solution is more or less same. but if it is 10 to the power 4 or 10 to the power 5 or 10 to the power 6, in that range it changes, or even smaller than that it changes. But when the Reynolds number reach to that limit, the solution do not change. These equations we have considered or derived considering that the wall is straight. Okay, for 3 dimensional case, you can extend the equation very easily in the same form, you can do it yourself without any difficulty. For curved wall case, that normal momentum equation, that is dP dy equal to 0, that needs a little modification. When the wall curvature is considerable, not small curvature like the curvature that an airfoil has, for that type of curvature it is not required, but if the wall has very large curvature, then that equation needs to be changed, and the approximate form of that equation will become if the curvature is small enough, then this is not required, you can set straight you make it 0, dP dy equal to 0, but if the curvature is large, then one need to use this equation, replace that dP dy equal to 0. Now, so the final form of the boundary layer equations we are again using the dimensional form, not the non-dimensional form. So, these are the boundary layer equation. If you look to the equations compared to the full Navier-Stokes equations, they are definitely much simpler. Compared to the original equations, the original Navier-Stokes equations, when you compare to them, these equations are definitely simpler. However, if you compare to the inviscid flow case, where the only equation is Laplacian phi equal to 0, obviously compared to that these are difficult. We now have 3 separate equations, and remember we can't use velocity potential here. This is a rotational flow, the boundary layer flow is rotational flow. So, phi or the velocity potential is not defined. Not only that, within the boundary layer you can't even use your so called Bernoulli's equation, that p plus half rho u square equal to constant, that cannot be used within the boundary layer. You can use it at the edge of the boundary layer and outside the boundary layer, but not within the boundary layer. Within the boundary layer, which is rotational flow. So, if you want to use p plus half rho u square, that constant will change from streamline to streamline. Can you say that what will happen to the total pressure within the boundary layer? Within the boundary layer, what will happen to the total pressure? We already have dP dy equal to 0, meaning the static pressure P is remaining constant within the boundary layer as you move from the edge of the boundary layer to the wall. Okay. Considering a simple case, say this, say this is the edge of the boundary layer, an exaggerated view. So, the pressure is P is constant in this part. At any point here, here, or if we have large number of points, at each of these points P is same. The static pressure is same. What will happen to the total pressure? As you move to the wall from the edge of the boundary layer, as you move to the wall, what happens to the total pressure? This is a very simple question. It decreases. Total pressure is, in an inviscid flow, the total pressure is P plus half rho u square. P is constant and u we know is decreasing. As you move to the wall, u is decreasing. So, half rho u square is decreasing. So, the total pressure or stagnation pressure is decreasing as you move to the wall, stagnation pressure is decreasing. In an inviscid flow, the stagnation pressure always remain constant. In an inviscid flow, the stagnation pressure always remain constant, it does not change. But in the viscous flow, we see that the stagnation pressure changes, and as we move from the edge to the wall, the stagnation pressure decreases. Now, before we start thinking of solving this equation, let us look to some other boundary layer effect. Due to the presence of boundary layer over a solid wall, consider again a flat plate case. Due to the presence of the boundary layer, what happens? The velocity from the on the wall is 0, it gradually increases, and at the edge of the boundary layer it reaches the inviscid flow solution. After that, of course, it remains same. If there would have been no boundary layer, then for the from the plate surface to infinity, everywhere there would have been the inviscid flow solution. Okay. So, however, in this case you see that there is a small region where the velocity is less than what it would have been in an inviscid flow. Agreed? If we had an inviscid flow, say if you had an inviscid flow, say this is the plate, everywhere the flow velocity is, say the inviscid flow solution. Okay. For all this part, our flow velocity is, let us call it that inviscid flow solution U E. In our viscous flow, the velocity is 0 on the wall and then increasing gradually, and then if we consider this, up to certain distance the velocity has decreased and then it has increased and remained constant. Okay. But in this part the velocity is smaller. Can you see now that due to the presence of this boundary layer or due to this viscous effect, the total mass flow will be little less in this case. The total mass flow will be little less in this case. You see that there is a deficit or defect in the total mass flow. In an incompressible flow, mass flow is equivalent to volume flow. So, you can say that there is a deficit of volume flow. Or volume flux, whatever you go. Actually it is mass flow, but since incompressible flow, mass flow is analogous to volume flow. And how much is that? How much is the mass flow defect or volume flow defect? How much is that? So, consider only the thickness of delta E, because above delta E it is again same. So, there is no difference, that part will be same. So, only up to delta E there will be difference. So, in the inviscid flow, how much volume would have flown through that length delta UE into delta. Unit width you can consider in course. So, the area would have been delta into 1. In the inviscid flow, the volume that would have flown through the thickness of layer delta is UE into delta, and in case of viscous flow this is which can also be written as but we really do not know delta. So, this upper limit delta is really not preferred, it is not a preferable quantity, we do not know what it is. However, we know that when y is more than delta, then u e minus u is 0. There is no difference between u e and u. The viscous flow and inviscid flow, they are same when y is more than delta. So, since for delta greater than y greater than delta, this integrand becomes 0. So, we can straightaway extend this integration. And this becomes so, this is the amount or this is the volume of fluid that will flow less because of the viscous effect. This amount of volume will not be able to flow. If we compare between an inviscid and viscous flow, what you see that this is the amount of fluid that will not be able to flow due to the effect of viscosity. This of course has a unit of length, as you can see this integration 0 to infinity 1 minus u by u e dy, it is basically a length, and let us denote this length as delta star. So, u e delta star is the amount of fluid that has been blocked by viscous effect. U e into delta star is the amount volume of the fluid that has been blocked by the viscous effect. This is also another net effect of viscosity or boundary layer, or we can say vorticity, whatever we call it. Now, what is u e delta star? This volume flow, we can think it this way, that we have an inviscid flow, a purely inviscid flow, whose wall is raised by a distance delta star. We could have got the same thing as far as mass flow is concerned. If we consider that purely inviscid flow and we are concentrating only on getting the mass flow effect, then if we raise this wall by a thickness delta star, then also we will get the same amount of mass flow. Other way we can see that the effect of this boundary layer to introduce some amount of thickness to the plate, as if the plate has been thickened by a length delta star. So, that is another effect of the boundary layer, that because of the boundary layer we can see this equivalent effect is that the wall thickness has increased by delta star, or wall is displaced by a distance delta star, and this thickness, this delta star, it is called a displacement thickness. And as you can see, it is a very easily measurable quantity. You will be measuring delta star in your experiments later. So, you can see as is the wall is not really shifted, is equivalent. Do not think that the wall has really moved. no, wall is not going to move. It is equivalent effect in terms of effect as if it is shifted. That is what we had the plate like this, the original plate, to the finally the plate will appear like this, as if the plate now has a thickness. So, this is the apparent, this is the real plate and this is the apparent plate. Apparently, the plate has got a thickness. And of course, it has become slightly curved, because this delta star or delta is not constant throughout the plate length, it changes. This delta star is called displacement thickness. Look to it in another way. Consider the continuity equation. Okay. Consider continuity equation. We have dV dy equal to minus du dx. Integrate this between 0 to delta or 0 to infinity, it does not make much difference. Integrate across the boundary layer. What is this left hand side? Left hand side can be integrated explicitly. V at delta, V at 0 is 0, V at 0 is 0, so V at delta, that equal to zero. The right hand side is 0. Right hand side bring it in the form of delta star. And since we are integrating across y, then these quantities are no longer function of y. So, this derivative we can write as a ordinary derivative. Yes, what you have got? Yes? VE. How VE has come here? UE? UE into delta star minus delta. How you got a delta star minus delta? Since you have got a delta star, you must have brought in UE also here. Okay? And once it is UE minus U, that integration you have got, the limit can be straightaway extended to infinity. And definitely you have done it, because you have got delta star. Make it UE minus U, extend the integration to infinity. And the constant term that you are using, that derivative is 0. You are adding a constant term here, no, to get it delta star form. You are adding a constant here, and the derivative of that constant is 0. Minus what? UE into why delta? Why delta? It is a constant, it is not delta. It is not a constant, it is not delta. Where is delta coming? Let us say this is this integration UE dy extended and that constant derivative of that constant is 0. So, eventually this is what is this. or it becomes now see this is a can be thought of in another way. B E is the normal component of velocity at the edge of the boundary layer or where the inviscid flow solution starts. So, this happens to be the boundary condition for the inviscid flow. So, our original inviscid flow boundary condition was a 0 normal flow, V is 0 on the wall, U is anything, B is 0. Now, what we have got? U is still anything, but for V we have got something which is related to the boundary layer. So, in other way that the effect of the boundary layer is to modify the normal boundary condition. And since a normal flow is added, so it is equivalent to a source distribution, as if a source is distributed on the wall. So, this is also another effect. So, these are two alternative. This is the alternative effect to the inviscid flow. The inviscid flow will see either way, that either that the wall has now got a thickness or the wall has been displaced by a distance delta star, or it will see that okay, there is an additional source distribution placed on the plate whose strength is given by this. So, if as we mentioned earlier that in an interacting situation where one affects the other, which is of course the natural case, that the inviscid flow affects the viscous flow and viscous flow in turn affects the inviscid flow, either of these two approach is to be used for interaction. That is, say you are solving viscous flow by this approach. First you solve the inviscid flow using a 0 normal boundary condition. At this stage you do not have any boundary layer. You find the pressure distribution or velocity distribution on the surface, which is to be treated as the velocity or pressure on the edge of the boundary layer. Using that velocity and pressure, you now solve the boundary layer equation. Once the boundary layer is solved, you will find the delta star or this quantity, either of these two. You may use delta star, that means then you change the thickness of your body at delta star and recalculate your inviscid flow on that new body, again using 0 normal boundary condition. Alternately, you use another source distribution, add another source distribution which is given by this, but your body remains the same, body remain as it was earlier, but your source distribution has changed, and this is the way to proceed until convergence. Now, this is what we consider a defect in mass flow. Similarly, as you can understand that it will create defect in momentum flow as well as energy flow. Consequently, there is a thickness associated with momentum defect as well as energy defect. So, there are various type of boundary layer thickness. This is displacement thickness. Then if we consider a momentum deficit, there will be a momentum thickness. Then if we consider energy deficit, this will be taken as energy effect. If there is a temperature variation taken into account, then we will get a thermal boundary layer where temperature will change. Then that thermal boundary layer has its own length or own thickness. So, we will consider a few more cases and then perhaps look for solution or some other approaches.